Good evening, everyone. Good evening. Good evening. Very good evening to all of you. So, am I audible and visible? Please inform me in a chat box. Video and audio both are okay. Video and audio both are okay. Okay, so shall we start today's session? So, beta, whatever we discussed in a previous class, I hope everything is clear to you, right? Whatever we discussed in the previous class, I hope every part is clear to you, right? Every concept, right? Also numericals, everything is clear to you. Okay, so let's start today's session with some problem based on the previous concepts. Okay, so just 1 minute na? I think diagram is missing in this question. Diagram is missing, so just 1 minute. Okay, so let us consider this is the top plate. This is the top plate. This is bottom plate, right? And bottom plate is fixed. Bottom plate is fixed. And top plate is moving with velocity of constant velocity of 5 meter per second, right? And about this plate, about the bottom plate, there is a fluid number 1. There is a fluid number 1. So let us consider this is a fluid number 1. Right, this is the fluid number 1. And there is another fluid. Let us consider this is the fluid number 2. Right, and this fluid, let us consider this fluid having viscosity 3 poise. This fluid having viscosity 3 poise, and this fluid having viscosity that is 2 poise, right? And depth of this fluid, let us consider this is 2 mm. Let us consider this is 2 mm, and depth of this fluid, let us consider this is 1 mm, right? So what is the power P? What is the power P required to pull the top plate with constant velocity of 5 meter per second? The contact area of the top plate is 1 meter square, right? Contact area of top plate is 1 meter square. Assume linear velocity profile. So in question, the power required to pull the top plate is asked. Okay, try to solve this question. We already discussed concept related to this problem, so try to solve this problem. Try to solve this problem. We already discussed concept related to this problem, right? So try to solve this problem. In this question, it is clearly mentioned that velocity profile is linear, right? In this question, it is clearly mentioned that velocity profile is linear. So if you draw the velocity profile, if you draw the velocity profile, so this is the velocity profile, right? See, this is the velocity profile, right? This is the velocity profile, something like this. Something like this. Right, this is the velocity profile. Right, so what is the power which is required to pull the plate? Power required to pull the top plate. Power required to pull the top plate. So simply we can write this is the shear force on top plate. Simply we can write shear force on top plate multiplied by velocity of the top plate, multiplied by velocity of the top plate. Right, this is the power. Right, now this is equal to, now what is the shear force experienced by the top plate? What is the shear force experienced by the top plate? So simply we can say shear force experienced by the top plate is shear stress on top plate multiplied by area multiplied by, this is the velocity of the top plate, and that is given, right, 5 meters per second. So this is the power which is required to pull the top plate. Shear stress on top plate multiplied by area multiplied by velocity. Now calculate the shear stress on a top plate. So for calculation of shear stress experienced by the top plate, we have the Newton's law of viscosity, correct? We have the Newton's law of viscosity. So apply the Newton's law of viscosity. So if you apply the Newton's law of viscosity, so let us consider, beta. Let us consider this is the fluid number 1 and this is the fluid number 2. Let us consider. Right, let us consider this is the fluid number 1 and this is the fluid number 2. So what is the shear stress experienced by the top plate? We can write this is the mu1 multiplied by this is V minus Vi, right, V minus Vi divided by, right, divided by, let us consider this is H1 as H1 and let us consider this as a H2. Right, so H1 V minus Vi by H1 multiplied by V. Right, now in this expression, if you see this expression, the only unknown is Vi, right, the only unknown is Vi. So calculate Vi, right, calculate Vi. In this expression Vi is the unknown, now in this expression Vi is the unknown, so calculate Vi. So how you calculate Vi? How you calculate Vi? In previous class, how we calculated the Vi, interface velocity, right? What is the Vi? That Vi is the interface velocity. Let us consider this is the interface of both the fluid and here the velocity is Vi. So in previous class, how we calculated this interface velocity? How we calculated this? Right, so it is very simple, na? At the interface layer, we can say tau 1 is equal to tau 2. Tau 1 is equal to tau 2. Right, at the interface layer, the tau 1 is equal to tau 2. I already explained this part. Right, tau 1 is equal to tau 2. So what is the tau 1? So we can write this is the mu1 into this is V minus Vi, right, V minus Vi divided by H1 from the Newton's law of viscosity, and this is equal to, what is the tau 2? What is tau 2? What is tau 2? So tau 2 is equal to, this is mu2 into, see, mu2 into Vi minus 0, Vi minus 0 divided by, this is H2. So calculate Vi from this expression, beta. Right, calculate Vi from this expression. So see, mu1 is given 3 poise. Mu1 is given 3 poise. So this is 3 multiplied by, right, and V is 5 meter per second. So this is 5 minus Vi divided by. Now what is the H1? That H1 is 2 mm. H1 is 2 mm. H1 is 2 mm, and this is equal to, what is mu2? Mu2 is 2 poise. Mu2 is 2 poise into Vi divided by, what is the H2? That H2 is 1 mm. 1 mm. So calculate Vi from this expression. Calculate Vi. So you can say this is the 2 Vi, or simply this is 3 into 5 minus Vi is equal to, this is 2 2s are 4, 4 Vi, right? So this is 15 minus 3 Vi is equal to 4 Vi. So Vi is equal to 15 divided by 7, right? And this is 2.1 something, right? What is the exact Vi? That is 2.14 meter per second. Yes, right? 2.14 meter per second. So this is the Vi. This is the Vi. Is it clear to everyone now? This is the Vi. And once you know the Vi, then then you can easily calculate the power required to pull the plate, right? Now this is equal to mu1. So mu1 is 3 poise. So 3 poise in SI unit, this is 0.3 Newton second per meter square. 0.3 Newton second per meter square into, what is V? V is 5. Vi we already calculated, 2.14 divided by, what is H1? That H1 is 2 mm. So this is 2 into 10 to the power minus 3 into what is V? V is 5. So calculate power, and that power you are getting in watt. So calculate power from this expression. Calculate power. What is the power that you are getting? What is the power that you are getting? What is the power? Right, this is 2.142 meter per second. 2.142 meter per second. So what is the power? Tell me. Okay, so it's simple. This is 5 minus 2.142, 2 into 10 to the power minus 3, right, into 0.3 into 5. How much you are getting? Yes, very good. It comes 2.143 kilowatt. This is 2143.2135 watt, and in kilowatt it is 2.1435 kilowatt. So everyone getting the same answer? Tell me, everyone getting the same answer? Everyone getting the same answer? Please type in a chat box. Everyone getting the same answer? Everyone getting the same answer? That is 2.14 kilowatt. This is the answer. Right, so we already explained, we already discussed concept behind this problem in previous class. So this is the numerical based on that concept. So beta, I already told you there is no need to remember any formula. Right, there is no need to remember any formula, right? Just solve the problem from very basic. Right, what I am doing here, I am solving the problem from very basic. See, right? So I hope you can understand this. Fine. Now come to the next case. I think we discussed this part, case number 1. This is the case number 2, case number 3, case number 4. Now come to the beta case number 5. Come to the case number 5. Right, come to the case number 5. So what is the case number 5? In a case number 5, there is a block, right, and that block is sliding in a vertical gap. So let us consider a vertical gap. Let us consider vertical gap. Beta, so this is the vertical gap. Right, this is the vertical gap. Right, and in this vertical gap, a block is sliding. right? This is the vertical gap, and in this vertical gap, let us consider there is a block. This is the block, and this block is sliding, right? This is the block, and this block is sliding. And to minimize the friction between this wall and the block, right? Minimize the friction between the wall and the block surface, we provided a lubricant. We provided a lubricant like this. We provided lubricant like this. We provided lubricant like this. Just 1 minute. Huh? Just 1 minute. Just 1 minute. Okay. So okay, so this is the block. This is the block. Okay, this is the block. And to minimize the friction between the wall and the block, a lubricant is provided. See, lubricant is provided like this. Lubricant is provided like this. Right, so in vertical gap, a block is sliding. So beta, let us consider this block having weight W. Right, let us consider block having weight W. Let us consider W. W is weight of the block. Right, what is the W? Let us consider W is the weight of the block. Let us consider W is the weight of the block. And this is the lubricant. This is the lubricant. This is the lubricant. And let us consider this lubricant having dynamic viscosity, that is mu. Right. So what is my objective in this problem? What is my objective in this problem? Right. My objective is calculation of terminal velocity of this block. What is my objective in this question? My objective is calculation of terminal velocity of this block. So you can say, sir, what is the terminal velocity? This is a new term for us. What is the terminal velocity? Right. What is my objective in this problem? Objective. In this problem, my objective is calculation of terminal velocity. Calculation of terminal velocity. Calculation of terminal velocity. So this is my first objective. Right? This is my first objective, calculation of terminal velocity. So what is the terminal velocity? Can anyone tell me what is the terminal velocity? Can anyone tell me what is this terminal velocity? What is this terminal velocity? What is the meaning of the terminal velocity? Yes, right. But terminal velocity means steady state velocity. Right? Terminal velocity means simple. Terminal velocity means steady state velocity. Right? Terminal velocity means steady state velocity, or we can say, right, corresponding to terminal velocity, there is no acceleration. So dv by dt is equal to 0, or we can say that acceleration is equal to 0. So when acceleration is equal to 0, right? So at that time, that velocity of this block is known as the steady state velocity, or you can say terminal velocity. So ultimately, what is my objective? My objective is calculation of terminal velocity. Is it fine? Okay. Now, are you able to draw the free body diagram of this block? Are you able to draw the free body diagram of this block? Are you able to draw free body diagram of this block? Okay, so this is the block, right? Now see, weight is given W, right? Weight is given W. So weight is acting in the negative y direction like this. Weight is acting like this. Weight is acting like this, right? This is the weight, right? And tell me, in this, if you draw the free body diagram of this block, so yes, weight is acting downward. Any another force? Any other forces in this block? Any other forces? Yes, yes, absolutely correct, beta. That is a shear force. Absolutely correct. That is a shear force. And shear force is acting in an upward direction because block is moving in the downward direction. So the resistance force or shear force is acting in upward direction. So shear force is acting like this. So let us consider this is the Fs1 and let us consider this is the Fs2. Right, and since it is a symmetric problem, so simply we can say Fs1 is equal to Fs2. There is no problem with that, right? Since it is a symmetric problem, so simply we can say that Fs1 is equal to Fs2, that Fs1 is equal to Fs2. Okay, now can we write equation of motion? Yes, absolutely we can write. So from equation of motion, the summation Fy is equal to, that is MAy, right? Summation Fy is equal to MAy. This is the equation of motion. And since our focus on calculation of the terminal velocity, and at the corresponding to the terminal velocity, that acceleration is 0. Corresponding to the terminal velocity, acceleration is 0. So acceleration part is 0. Acceleration part is 0 because we are focusing on the steady state velocity. So simply we can write the summation Fy equal to 0. Okay. Now see, weight is acting downward, so this is minus W. Weight is acting downward, so that is minus W plus this is 2 times of, right? Fs1 is equal to Fs2 is equal to, simply we can write Fs1 is equal to Fs2 is equal to, simply we can write, let us consider this is the Fs. So this is 2 times of Fs. 2 times of Fs. We can say this is 2 times of Fs and this is equal to 0. So simply we can write W is equal to, this is 2 times of Fs. Now tell me guys, are you able to find out the shear force? Are you able to find out the shear force? Are you able to find out the shear force? Tell me. Are you able to find out the shear force? Are you able to find out the shear force? Right. So for the calculation of the shear force, we have Newton's law of viscosity, right? For the calculation of shear force, we have Newton's law of viscosity, right? And as per the Newton's law of viscosity, we know that shear stress experienced by the any layer is equal to, that is mu du by dy. And for calculation of du by dy, you must know the velocity variation in this gap. You must know the velocity variation in this gap. So beta, let us consider this gap, right? Let us consider this gap as h, and also in this direction, let us consider this gap as h, right? Gap is considered as h. So for calculation of the shear force, you must know the velocity variation in this gap, right? And I already told you, if velocity variation is not mentioned in the problem, then consider as linear variation, right? Then consider as linear variation. So if you focus in a particular this part, let us consider in this particular part, if you consider in this particular part, and if I exaggerate this part, now see here, this portion is, this part is a fixed part, this is fixed part, and there is a liquid, lubricant, this is the lubricant, this is the liquid lubricant, and if you see the variation, if you see the velocity variation, if you see the velocity variation, so beta this is the velocity variation, this is the velocity variation, see, this is the velocity variation, right? This is the velocity variation. So I already told you, if velocity variation is not mentioned in the problem, then consider linear velocity variation. Okay, and this velocity is the v, this velocity is the velocity of the block, and the velocity of the block, that is v, is that or terminal velocity. Let us consider this is the vt, terminal velocity. Since we are discussing the things corresponding to the terminal velocity, so let us consider this velocity as a vt. So what is the vt? That vt is a terminal velocity of the block, right? What is the vt? That vt is terminal velocity of the block. Vt is terminal velocity of the block. Fine. Now, can you find the fs? Can you find the fs? Can you find the fs? So what is the fs? What is the shear force? So that shear force is equal to, right? The shear force is equal to, you can say this is the shear stress multiplied by area. Which area? Area of the block which is in contact with the fluid. Which area? Area of the block which is in contact with the area. So let us consider this area as A. Let us consider this area as A. So what is the A? That A is the area of the block which is in contact with the fluid. Or you can say A is the area in which shear stress is acting, or shear force is acting. That is the area. Fine. Now see here. So Fs is equal to now tau is equal to, that is mu multiplied by du by dy. So since velocity variation is linear, so simply we can write vt minus 0 divided by gap. And what is that gap? That gap is h multiplied by area. So this is the shear force. So simply we can write, this is the W, we can write m into g, right? This is 2 multiplied by mu vt divided by h multiplied by a. So what is the vt? So from here you can calculate vt. So vt is equal to, simply this is the mgh divided by this is 2 mu a, right? This is the terminal velocity of the block. This is the terminal velocity of the block, right? This is the terminal velocity of the block, right? mgh upon 2 mu multiplied by area, right? So if someone asks you what is the terminal velocity of the block, so you can easily find out the terminal velocity of the block. So what is the terminal velocity beta? Terminal velocity is the velocity at which acceleration is 0, or simply you can say steady state velocity. So this is the first objective. First objective is calculation of terminal velocity of the block, right? Is it clear or not? Is it clear or not? Beta, that is h, na? Why we are considering the 2h? Because we already considered 2 here, na? Right? fs1 is equal to fs2. Right? And that is equal to fs. So we calculated fs2, and if you calculate the fs2, or when you calculate the fs2, then only h come into picture, na? The total shear stress is 2 times of fs. Total shear stress is 2 times of fs, or you can say the total shear stress is fs1 plus fs2. And since symmetric condition is there, so simply we can say fs1 is equal to fs2. So either you calculate fs1 or you calculate fs2, right? So I calculated the fs2, and what is the fs2? This is the fs2. Is it fine? Is it okay? Yes, okay. Fine. So this is the first objective. Now beta, can you tell me can you tell me what is the variation of, see, initially if I'm talking about this block, initially if I'm talking about this block, initially what is the velocity of this block? That initially the velocity of the block is 0, right? Initially velocity of the block is 0, and after some time the velocity reaches to terminal velocity. So before attaining the terminal velocity, can you tell me how the velocity of the block varies with time? How the velocity of the block varies with time, right? See, terminal velocity attains after some time, right? Initially velocity of the block is 0. After some time it attains the terminal velocity, or you can say steady state velocity. So can you tell me in between right, in between 0 to terminal velocity, how the velocity varies with respect to time? Can you tell me? Are you getting my question or not? Are you getting my question or not? Are you getting my question or not? Question is clear or not? Tell me. Question is clear or not? So beta, my question is simple. How the velocity, what is the relation between velocity versus time? Right? How the velocity of the block changes with time? How the velocity of the block, how velocity of block changes with time? This is my question. So I know initially the velocity is 0. I know initially block velocity is 0. After some time velocity reaches the terminal velocity, right? So once terminal velocity reach, then velocity is not changing with respect to time. But what happened in between 0 to Vt? Right, so this is my question. So how velocity of the block changes with time? How velocity of the block changes with time? This is my question. So are you able to answer this question? Are you able to answer this question? So it is very simple. Start from equation of motion. Start from equation of motion. So from equation of motion. From equation of motion. From equation of motion. From equation of motion, the summation Fy is equal to, this is simply m ay. We can write like this. Right, now summation Fy, what is the summation Fy? Right, W is acting downward. W is acting downward. W is acting downward. So let us consider this is mg minus this is 2 times of Fs. 2 times of Fs is equal to, this is m multiplied by dv by dt. We can write in this way now. We can write in this way now. Tell me. We can write in this way now. Right, mg minus 2Fs is equal to m multiplied by dv by dt. That expression A is equal to dv by dt. Right, now see here, that mg, or simply we can write that mg is mg minus 2 multiplied by, now what is the Fs? What is the Fs? So Fs we can write mu multiplied by v minus 0. V minus 0, right? Or just 1 minute beta, just 1 minute. Right, 2 multiplied by, this is tau multiplied by area is equal to m multiplied by dv by dt. Right, now mg minus 2 into, what is the tau? What is tau? The tau is mu multiplied by v minus 0 divided by h multiplied by area is equal to, this is m dv by dt. So we can write in this way, mg minus, this is 2 mu va divided by h is equal to, this is m dv by dt. Right, we can write in this way. So till this point it is clear to everyone. 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 Now beta see. If you see this expression, if you see this part, that mu is constant, mu is not changing with respect to time, area is constant, area is not changing with respect to time, h is constant, h is not changing with respect to time. So let us consider, let a constant, let us consider that is k. So k is equal to 2 mu, right, a divided by h. Since 2 is constant, mu is constant, a is constant, h is constant, so this I considered as another constant, and let us consider that is k. So we can write this is the mg minus that is k into v is equal to m dv by dt. Or simply we can say that dv by dt is equal to this is g minus or do one thing, na? Or do one thing, just 1 minute, do one thing because beta m is also constant, na? Just do one thing like this, just 1 minute, right? Do one thing, m, right? So this is g minus, this is 2 mu v a divided by h m dv by dt, right? Now take 2 mu a m h is equal to k. So simply we can write this is equal to, this is g minus v by, or g minus k into v is equal to dv by dt. So till this point it is clear to everyone? Till this point it is clear to everyone? Tell me, till this point it is clear to everyone? What is my objective? My objective is find how the velocity of the block changes with time. This is my objective. So start from the equation of motion, from very basic. Start from equation of motion, from very basic. Is it clear or not? Okay, so dv by dt, we can write that dv by dt is equal to, this is g minus kv. Now apply variable separable method. So this is dv g minus kv is equal to dt. Right, now perform integration. Simple. Ultimately what is my objective? My objective is calculation of variation of block velocity with respect to time. This is my objective. Now perform integration. So if you perform integration, so apply the limit. So beta at time t is equal to 0, what is the velocity of the block? At time t is equal to 0, what is the velocity of the block? At time t is equal to 0, what is the velocity of the block? At time t is equal to 0, what is the velocity of the block? That is 0. At any time t, what is the velocity of the block? That velocity of the block is v. Right? At any time t, what is the velocity of the block? Velocity of the block is v. Okay. Now you know integration of this, na? You know the integration of this, na? dx a plus bx. You know the integration of this, na? What is the integration of this? What is the integration of this? What is the integration of this function? What is the integration of 1 upon a plus bx? What is the integration of this? You know na? Right, so can we write this is beta 1 upon b ln a plus bx, na? Yes or no? What is the integration of a plus bx? That integration of a plus bx we can write now 1 upon b ln a plus bx. And if you see this function 1 upon g minus kv, so that is similar to this only, right? So we can say this is 1 upon minus k ln g minus kv, and what is the limit? The limit is 0 to v, and this is equal to t minus 0. So simply we can write t is equal to right, this is minus 1 by k, and this is ln ln g minus kv, ln g minus kv minus ln g. Right. So we can write in this way. Is it clear or not? Is it clear or not? Tell me. Is it clear or not? Tell me. So simply we can write t is equal to this is minus 1 by k, and this is ln g minus kv upon g. Right. Now, if you arrange the terms, then we can write, just 1 minute, this is kt, right? This is minus kt, right? Minus kt, and this is equal to ln 1 minus kv by g, right? So 1 minus kv by g is equal to, right, this is e to the power minus kt, and kv by g is equal to 1 minus e to the power minus kt, or we can say v is equal to this is g by k, 1 minus e to the power minus kt. So this is the variation of v with respect to, this is the variation of v with respect to time. This is the variation of v with respect to time. This is the variation of v with respect to time. Right. V is equal to g by k, 1 minus e to the power minus kt. So beta, how the velocity of the block changes with respect to time? How the velocity of the block changes with respect to time? How the velocity of the block changes with respect to time? Tell me. How the velocity of the block changes with respect to time? It changes exponentially. It changes exponentially. It changes exponentially. How the velocity of the block changes with respect to time? The velocity of the block, from this mathematical expression it is clear na, that velocity of the block changes exponentially, with time, right? And when time t is equal to infinity, see, when time t is equal to infinity, now see, just 1 minute, that v is equal to g by k na, v is equal to g by k, 1 minus e to the power minus kt. And what is the k that k is equal to? What is the k that k is equal to? K is equal to 2 mu a upon mh. 2 mu a upon mh. This is k. Right, and we know that beta, when t tends to infinity, then we know that e to the power minus infinity is, when t tends to infinity, we know that na, e to the power minus infinity is 0. So ultimately what you are getting, that is g by k. And what is k? So you put here k is, this is the 2 mu a upon, this is the mh, or simply you can write this is the mgh upon 2 mu a. So when t is equal to infinity, then this velocity is nothing but the terminal velocity. When t is equal to infinity, then v is equal to vt. Right? See this expression. Right? mgh upon 2 mu a. Now see here, mgh upon 2 mu a. So when t is equal to infinity, then V becomes Vt, and what is the Vt? That Vt is mgh upon 2 mu a. So if you see the velocity variation with respect to time, if you see velocity variation with respect to time, so let us consider this is the velocity axis and this is the time axis, right? Now see, the velocity variation is something like this, right? The velocity variation is something like this, and beta, this is nothing but the, see, this is nothing but the terminal velocity. This is nothing but the terminal velocity. This is the Vt, right? This variation is exponential variation. This variation is exponential variation. This variation is exponential variation. And once velocity reaches Vt, then velocity is not changing with respect to time. Is it okay? Is it clear or not? Tell me. Is it clear? Is it clear to everyone? Okay. So beta, this is the interview question basically, right? Up to here, this is the gate problem, right? Up to here, this is the gate problem. In most of the cases, in question, terminal velocity is asked, right? So this is the gate problem, and beta, this is the interview problem, right? This is the interview question. How velocity changes with respect to time? How velocity changes with respect to time? This is mainly interview question. Okay, now come to the next case, case number 6. Come to the next case, and that is case number 6. So there is a block, and that block is sliding in a inclined plane, right? There is a block, and that block is sliding in a inclined plane. So let us consider an inclined plane like this, right? Let us consider an inclined plane like this. This is the inclined plane, right? This is the inclined plane, and this inclined plane is at an angle theta from the horizontal. This inclined plane is at an angle theta from the horizontal, right? Now there is a block. There is a block. Let us consider this is the block. Let us consider this is the block, and this block is sliding, right? This block is sliding in this inclined plane. There is a block, and this block is sliding in this inclined plane. So better to reduce the friction between the block surface and the plane, right? To reduce the friction between the block surface and the inclined plane, what I am doing here, I am providing the lubrication. What I am doing here, I am providing the lubrication like this. So this is the lubricant, right? This is the lubricant, right? This is the lubricant. And let us consider the thickness of the lubricant. Let us consider the thickness of the lubricant is H. Let us consider thickness of the lubricant is H. And the area of the block, which is in contact with the lubricant, the area of the block which is in contact with the lubricant, let us consider that area is A. Okay. Okay, now this block is sliding, right? This block is sliding. So what is my objective here? My objective is calculation of terminal velocity of this block. What is the terminal velocity of the block? What is my question here, or what is my objective here? My objective is find the terminal velocity. Find the terminal velocity of the block. This is my objective. Find the terminal velocity of the block. Right, this is my objective. So to find the terminal velocity of the block, okay, just 1 minute, just 1 minute. What is the weight of this block? So let us consider weight W. W is weight of the block. Right, what is the W? W is weight of the block. W is the weight of the block. So what is my objective here? My objective is calculation of terminal velocity of this block. And what is the terminal velocity? We know that terminal velocity is the steady state velocity or velocity at which acceleration is 0. Okay, so first better draw the free body diagram of this block. First draw the free body diagram of this block. First show the forces acting on this block. Right, so this is the block. This is the block. And let us consider these are the reference axes. Right, these are the reference axis. Okay, now block is sliding in this direction. Now block is sliding. Let us consider this is the negative y direction, this is positive y direction, this is positive x direction, and this is the negative x direction. Let us consider. So block is sliding in the negative y direction. Block is sliding in the negative y direction. So what about the shear force or resistance force acting on this block? What is the direction of shear force or resistance force? What is the direction of shear force or resistance force? What is the direction of shear force or resistance force? Obviously that is in upward direction. Obviously that is acting in the upward direction. Okay, so this is the direction of shear force. This is the direction of shear force. This is the direction of shear force. Right. Now W is the weight of the block. So W is acting in the downward direction. We know that. How W is acting? How weight is acting? So weight is acting like this. Weight is acting like this. Weight is acting like this. Right. Now if you write the equation of motion, so simply we can write the summation Fy is equal to MAy. If you write the equation of motion, so simply we can say summation Fy is equal to M into Ay. Right. And what is the Ay? That Ay is 0, because we are talking about the terminal velocity. Right. We are trying to find out the terminal velocity. So what is the acceleration? That acceleration is 0. That acceleration is 0. So simply we can write the summation Fy equal to 0. Summation Fy equal to 0. Right. Now resolve this W in x, in x and y direction. So if you resolve this W, so better first find out the angle theta. Right. Angle between these two planes is theta. So angle between the perpendicular of this plane is also theta. Right. So this is the perpendicular. Just 1 minute. Just 1 minute. This angle. Right. This is the perpendicular of this, and this is perpendicular of this. So this angle is also theta. This angle is also theta. Na? This angle is also theta. This angle is also theta. This angle is also theta. So if you resolve W into two components, so this is one component W, and this is the another component of W. Right, this is the one component of W which is normal to the plane, and this is the another component of W which is parallel to the plane. And this component is W cos theta, and this component is W sin theta. Right, this component is W cos theta, and this component is W sin theta. So summation Fy equal to 0 and summation Fy equal to 0. So simply beta, this is minus W sin theta plus Fs is equal to 0. So simply we can say Fs is equal to, this is W sine theta. Right, Fs is equal to W sine theta. But what is my objective? My objective is calculation of terminal velocity. Right, my objective is calculation of terminal velocity. So from the Newton's law of viscosity, we know that the shear stress at any y is equal to mu du by dy. So to calculate the shear force, or to calculate the shear stress, we must know the velocity variation in this gap. Right? For the lubrication or for the lubricant, we must know the velocity variation, how the velocity varies in this particular gap H. So I already told you, if velocity variation is not given, then what? If velocity variation is not given, then if velocity variation is not given, then assume linear velocity profile. Right? Then assume linear velocity profile. So if velocity variation is not given in the problem, then assume linear velocity profile. Otherwise, you are not able to solve the problem. So assume linear velocity profile. Assume linear velocity profile in gap. Assume linear velocity profile in the gap, because without assuming linear velocity profile, it is not possible to solve this problem. Right? If you don't know the velocity variation, then how you calculate this du by dy? Are you getting my point? If you don't know du by dy, if you don't know the velocity variation with respect to y, then how you know the du by dy? I hope you can understand this. Okay. Now see, if I exaggerate in this particular part, let us consider this particular part. So see beta, this is the plane, right? This is the plane, and above the plane there is a lubricant. Right? Block is sliding with terminal velocity Vt. So if you see the velocity variation, here, see, if you see the velocity variation in the gap H, so beta, this is the velocity variation. Right? This is the velocity variation. Right? This is the velocity variation. This is the Vt, and this gap is H. Fine. Now, what is the du by dy? So for linear velocity profile, simply we can write, this is mu multiplied by, right, this is Vt minus 0 divided by, what is the gap? That gap is H. Okay, so tau, that is mu, and we know that if velocity profile is linear, then each layer experiences the same shear stress. So if I'm talking about the layer which is in contact with the block, that layer also experiences the same shear stress, which is mu Vt by H. Right? Now we know that what is the Fs? Fs is tau multiplied by A, and this is equal to W sine theta. So tau, this is mu into Vt, right? Mu Vt H multiplied by A is equal to W sine theta. Okay, now calculate Vt. So this is simply W sine theta into H divided by, that is mu A. Or you can say Vt is equal to, this is mgh, right? Mgh, W is m into g, so this is mgh sine theta divided by mu A. Right? So this is the terminal velocity. This is the terminal velocity of the block. And before attaining the terminal velocity, How the velocity varies with respect to time? Before attaining the terminal velocity, how the velocity changes with time, how the velocity changes with time. So that is the same variation, that is the exponential variation only. That is the same variation, exponential variation only. Okay, so beta, this is the case number 6. Is it clear to everyone? Tell me, is it clear to everyone? Case number 6. Okay, if this is clear to everyone, then try to solve this problem. Then try to solve this problem. Then try to solve this problem. If this concept is clear to everyone, then try to solve this problem. In this question also, terminal velocity is asked. In this question also, terminal velocity of the block is asked. A block with a base of 15 centimeter by 20 centimeter and weight 20 Newton is allowed to slide down a long inclined plane of slope 1 vertical, 5 horizontal. A thin film of oil of viscosity 1.5 poise and thickness 0.3 mm exists on the surface of the inclined plane. Right? What is the terminal velocity of the block? What is the terminal velocity of the block? What is the terminal velocity of the block? So beta, this is the inclined plane. This is the inclined plane. Right? This is the inclined plane. This is the inclined plane. And this is the horizontal, and this angle is theta. And for calculation of theta, that information is given 1 vertical, 5 horizontal. 1 vertical, 5 horizontal. Right? That means 1 vertical, 5 horizontal means 1 vertical, 5 horizontal means this is 1, this is 5. Right? 1 vertical, 5 horizontal means 1 vertical, 5 horizontal means this is 5. This horizontal is 5 and this vertical is 1. So you can easily calculate theta. You can easily calculate theta. So tell me, what is the theta? What is the theta? So this is simply tan theta is equal to tan theta, this theta, na? This theta is equal to this theta. So tan theta is equal to, this is 1 by 5. So calculate theta. So this is tan inverse 1 by 5. Right? Theta is tan inverse 1 by 5. Right? 11.53. 11.53. Everyone getting the same? 11.53 degree. Everyone getting the same? 11.53 degree. Fine. Now, this is the block. Right? This is the block. This is the block. Right? And in question it is mentioned what is the area, this area which is in contact with the fluid base, right? That this is 15 centimeter, this is 15 centimeter by 20 centimeter, right? And there is a lubricant, there is a lubricant, there is a lubricant. And what is the viscosity of this lubricant? What is the viscosity of this lubricant? That viscosity is 1.5 poise. 1.5 poise. 1.5 poise, right? And this thickness, that is H. And H is mentioned in the problem, right? The thickness is H, and H is mentioned in the problem, that is 0.3 mm. 0.3 mm, right? And beta, again in the gap velocity profile is not mentioned, so assume linear velocity profile in a gap. Assume linear assume linear velocity profile in the gap. Assume linear velocity profile in the gap. So linear velocity profile in the gap. So simply you can write summation Fy is equal to, this is the MAy corresponding to terminal velocity, that acceleration is 0. So summation Fy equal to 0. And simply we can write that Fs is equal to this is W sine theta. And what is the Fs? This is a tau multiplied by A is equal to W sine theta, right? And tau is, this is mu multiplied by Vt minus 0 divided by gap into A is equal to W sine theta. Okay, so calculate terminal velocity from here. So Vt, or just 1 minute, mu is 1.5 poise. So this is 0.15 Newton second per meter square into Vt is unknown multiplied by area. Area is 15 multiplied by 20, 15 multiplied by 20 into, this is 10 to the power minus 4 meter square divided by h. H is given 0.3 mm. So this is 0.3 into 10 to the power minus 3 meter. And this is equal to W sine theta. What is the value of W? 20. And what is the theta? That theta is 11.53. 11.53. Okay, so calculate Vt. There is a one equation and one unknown, and calculate Vt from this equation. Calculate Vt from this equation. So what is the Vt that you are getting? What is Vt that you are getting? What is the terminal velocity? Tell me, what is the terminal velocity? What is the terminal velocity? Tell me. 20 sine 11.53 0.3 into 10 to the power minus 3 0.15 into 15 into 20, right? 0.15, 15 into 20 into 10 to the power minus 4. Okay, how much you are getting? .266. I think there is some problem with the data. I think so. Because that Vt value comes very, very large, I think. 20 sine, just 1 minute, 20 sine 11.53 into 0.3 into 10 to the power, or 0.3, 10 to the power minus 4, 10 to the power minus 3. So 10 to the power minus 3, 10 to the power minus 3 cancel out into 10. And answer divide 0.15 into 15 into 20. 0.266. Sorry, 0.26 meter per second. This comes 0.266. 0.266 meter per second. Everyone getting the same answer? Everyone getting the same answer? Everyone getting the same answer? 0.266 meter per second. This is the answer. This is the terminal velocity. This is the terminal velocity, 0.266 meter per second. This is the correct answer. Fine. Okay, now come to the case number 7. Come to the case number 7. Case number 7. Now, in case number 7, force required to pull the shaft with constant velocity V in a sleeve. So let us consider there is a sleeve. Let us consider there is a sleeve. Let us consider there is a sleeve like this. And in the sleeve, right, this is a sleeve. Right, this is the sleeve. This is the sleeve. And in this sleeve there is a shaft. So let us consider this is the shaft. Let us consider this is the shaft. This is the shaft. Okay. And let us assume this diameter is small d. This diameter is small d. Or we can say, let us consider this diameter is di. And this diameter as d naught. This diameter as d naught. Right? And in this question, as in this case, what is the question? What is the force required to pull the shaft with constant velocity v? So we apply a force F on this shaft. We apply force F. We apply force F on this shaft, and this shaft is moving with constant velocity, that is v. Right? And to reduce the friction between the sleeve and the shaft, to reduce the friction between the sleeve and the shaft, there is a lubricant. There is a lubricant. So this is the lubricant. Right? This is the lubricant. And let us consider this lubricant having velocity, that is mu. Right? This is the sleeve. This is the sleeve. This is the shaft. This is shaft. Right? And what is my objective? My objective is calculation of F. What is the F? Right? So it is very simple, na? It is very simple. If you see here, right? If you draw the free body diagram of this shaft, if you draw the free body diagram of this shaft, if you draw the free body diagram of this shaft, okay, just 1 minute, just 1 minute. Let us consider length of the shaft as L. Right? Length of the shaft as L. Let us consider length of the shaft as L. Length of the shaft as L. Fine. So if you draw the free body diagram of this shaft, then it is very much clear. It is very much clear, right? Shear force acting on this shaft, right? Shear force acting on this shaft. So shear force acting like this. Shear force acting like this. Shear force is acting like this. Right? Shear force is acting like this. Right? Shear force Fs, shear force Fs. Right? And this shear force is acting around the circumference. This shear force is acting around the circumference, around the circumference, around the circumference, around the circumference. So beta, this is the shear force. This is the shear force. This is the shear force. And this shear force is acting around the circumference. Right? And if you see the side view, right? If you see the side view and see, if you see the side view, so this is the shaft, right? And that shear force is acting right? If let us consider perpendicular to the monitor, there is a length. Perpendicular to the monitor, there is a length like this, right? Like this. Perpendicular to the monitor, there is a length like this. Your shaft is like this. If you see, then this is the view, right? And if you see from the front, then this is the view. Or in this case, if you see from the side, then this is the view. From the side, this portion is visible. This portion is visible. Is it clear? So how the shear force is acting? How the shear force is acting? Shear force is acting along the length like this, in a circumference, because complete shaft is in contact with the fluid. Complete shaft is in contact with the fluid. Complete shaft is in contact with the fluid. So shear force is acting in a circumference along the length. I hope you can understand this. I hope you can understand this. Okay. Now see. So if you write equation of motion, summation fx is equal to, this is max. Summation fx is equal to max. Right? Now constant velocity, that means acceleration is 0. So this is 0. So simply we can write summation fx equal to 0. Summation fx equal to 0. Now summation fx equal to 0. So we can write this is plus f minus shear force fs is equal to 0. So simply f is equal to fs. Now find out the fs. Now find out the fs. Find out the fs. So fs is equal to, this is nothing but the shear stress multiplied by area. Which area? You can say shear area, or you can say area which is in contact with the fluid. Area which is in contact with the fluid. Right? So tau multiplied by A. Right? Now calculate tau. So for the calculation of tau, we have Newton's law of viscosity. So tau is equal to, this is mu du by dy. Tau is equal to mu du by dy. Now if you see the, at any section, if you see the velocity profile, now see, if you see the velocity profile, in the gap, velocity profile is not mentioned na. And what is this gap, beta? What is this gap? What is this gap? We can say this gap. What is this gap? What is this gap? Tell me. So complete gap is d naught minus di. So what about this h? You can say this is the d naught minus di divided by 2. Right? There is a concept, or there is a term, that is a diametral clearance. There is a term diametral clearance. What is the diametral clearance in this problem? What is the diametral clearance? Diametral clearance. What is the diametral clearance? That is d naught minus di. This is the diametral clearance. Right? There is another term, radial clearance. Radial clearance. There is another term, radial clearance. And what is the radial clearance? That is the r naught minus ri. R naught minus ri. Or you can say d naught minus di by 2. Right? The radial clearance is nothing but the d naught minus di by 2 only. Right? D naught minus di by 2. Or you can say r naught minus ri. Or you can say r naught minus ri. Right? So if you write Newton's law of viscosity, and from the Newton's law of viscosity, if you want to find out the shear stress experienced by the shaft, right? So draw the velocity profile, and if velocity profile is not mentioned, then we assume that is the linear velocity profile. We assume linear velocity profile like this. Right? So tau is equal to, this is mu multiplied by linear velocity profile. So this is v minus 0 divided by this is, you can write r naught minus ri. Right? So f is equal to, this is mu multiplied by v upon R naught minus Ri. And what is the A beta? What is the A? Can anyone tell me what is the A? Area which is in contact with the fluid. And what is the area? That area is 2 pi Ri into L. 2 pi Ri into L. So this is the force which is required. This is the force which is required to pull the shaft with constant velocity v, right? This is mu into v into 2 pi RIL divided by R naught minus Ri. Right? This is the F. This is the force F which is required to pull the shaft with constant velocity v. Is it clear? Is it clear? Tell me fast. Is it clear or not? Is it clear or not? Tell me. Is it clear or not? Tell me. Is it clear or not? Any doubt? Any doubt on this? Or you can write in this way also, no? You can write in this way also, no? F is equal to, you can write in this way also, that is mu v pi DIL, right? Mu v pi 2 Ri, so di, 2 Ri is equal to di. So pi DIL upon d naught minus di, right? You can write in this way also. You can write in this way also. But again I am telling you guys, this is not a formula. This is not a mathematical expression, or this is not a formula, right? It is just a concept. Right? So whatever the end result that you are getting, that is from the basic concept. Okay, so I hope you can understand this. Okay, now instead of this kind of sleeve, let us consider there is a tapered sleeve. Let us consider there is a tapered sleeve, right? Instead of this kind of sleeve, right? In this case, that H is constant, na? That gap is constant. This is the H, this is H. In this case, H is constant. But what happened with H is variable? That means, let us consider there is a tapered sleeve. Let us consider there is a tapered sleeve. So next case number 8, force required to pull the shaft with constant velocity v in a tapered sleeve. In a tapered sleeve means, see, beta, this is the shaft. This is your homework question. This is your homework question. Try this question. No? This is the shaft, right? This is the shaft. This shaft having diameter, this is a di, and there is a tapered sleeve. There is a tapered sleeve like this. There is a tapered sleeve like this. There is a tapered sleeve like this. This is the sleeve. Right? This is the tapered sleeve. Fine. And to reduce the friction, to minimize the friction, there is a lubricant film. There is a lubricant film. Like this. right? And let us consider this as H1, and let us consider this as H2. Here the gap is H1 and here the gap is H2. And what is the length of the shaft? The length of the shaft is L. What is the length of the shaft? Length of the shaft is L. So what is the force F? What is the force F required? What is the force required to pull this shaft with constant velocity V? This is the question. This is the question. So this is the problem. This is the problem where that H is constant. That H is constant, as H is not changing with respect to length. But in this case, H is changing with respect to length. So try to solve this problem. Right? Try to solve this problem. This is your homework case. Tomorrow, in tomorrow's class, I will discuss this. But before that, at least, you should try yourself. At least you should try yourself. Right? So this is di. That the diameter of the shaft is di. Length of the shaft is L. Right? You can say at x is equal to 0, that gap is H1, and at x is equal to L, that gap is H2. So question is, what is the force F? What is the force F which is required? What is the force F, or what is the force required to pull the shaft with constant velocity V? So first try this question to yourself. Right? Try to answer. Try to get answer of this question. If you're not able to solve the problem, don't worry. If you're not able to solve this problem, don't worry. In tomorrow's class, we will discuss this particular problem. Okay, so I think this is enough for today. Right? Tapered sleeve. Tapered sleeve. Tapered sleeve. This is shaft. Right? And this is the lubricant. This is the lubricant. And this lubricant having dynamic viscosity mu. This is the lubricant, and this lubricant having dynamic viscosity mu. What is my objective? My objective is find the force which is required to pull the shaft with constant velocity V. So this is my objective. Okay, so this is your homework problem. Okay, so I will discuss this problem in tomorrow's class. I will discuss this problem in tomorrow's class. So beta, I hope whatever we discuss in today's class, that is clear to everyone. I hope whatever we discuss in today's class, that is clear to everyone. Okay, so thank you so much. Thank you so much. Bye-bye. Take care. And good night, everyone. Good night. Good night.